Hello. In this video, we are going to study first-order linear differential equations. First, our definition. A first-order ordinary differential equation y prime equals f of xy is said to be linear in y if it can be expressed in the form y prime plus p of xy equals f of x, where the functions p and f have suitable common domain. What we intend to do here is to be able to solve such an equation. This is our goal. Before we embark in that goal, let me remind you of a calculus rule called the product rule that says that the derivative of the product of two functions my with respect to x being the independent variable, equals the first function m times the derivative of the second function dy dx plus the derivative of the first function dm dx times the second function y. More compactly, you can say the derivative of the product m times y equals m times the derivative of y plus the derivative of m times y. We're going to utilize the product rule in developing a solution method for a first order linear equation. Okay, so let's take a look at how to begin. So first, we begin with our equation y prime plus p of xy equals f of x, and we multiply it both sides by some undetermined function of x. We're going to call that function mu. So multiply left-hand side and right-hand side by mu. We get mu y prime plus mu p of xy equals mu f of x. The idea that we want to utilize in solving our differential equation is in making this new left-hand side the derivative of a product. What product do we want to say this is the derivative of? Well, it should be mu times y. So let's require mu y prime plus mu p of xy to be equal to the derivative of mu times y. So I'm highlighting that. So we want mu y prime plus mu p of xy to equal the derivative of the product of mu and y. Under that requirement, we shall obtain the following. If we develop the right-hand side formally by using the product rule, we know we obtain mu y prime plus mu prime y. This is just appealing to our rule. Instead of m, we shall use mu. So mu y, the derivative of that is mu y prime plus mu prime y. Mu y prime plus mu prime y. Now, here we in this new equality, in this equality that we have now, we can easily reduce the problem. Cancel mu y prime on both sides. So we end up with mu p of xy equals mu prime. Now, in this cancellation, of course, there was also the requirement that this portion must equal mu prime. So we end up with mu p of x equals mu prime. In other words, the derivative of mu with respect to the independent variable x is mu times p of x. Notice that what we are trying to solve here is for the unknown function mu. So we see that this is a separable equation. So separating the variables, we get d mu over mu equals p of x d of x. And we know how to solve this equation. Apply an integral on both sides. On the left side, we obtain the natural logarithm of mu. On the right side, we obtain formally the integral of p of x dx. If you solve for mu, then you end up with a mu equaling e to the integral of px dx. Okay, so we now have the undetermined function mu is actually mu equals e to the integral of px dx. So that is our method solution. Let's exemplify. Number one, solve. Well, first, in this example, we have determined whether the given first order ODE, determine whether the first order ODE is linear. For those that are linear, solve them as such. Okay, so here we go. In number one, y prime plus 1 over x plus 1y equals x. Y prime plus 1 over x plus 1y equals x. Observe that 1 plus 1 over x plus 1 is a function of x, and the right side x is also a function of x. So here we have a linear equation, y prime plus some function of xy equals some function of x. So it is linear. So now we solve it. The key to solving, of course, is finding this mu. Mu equals e to the integral of px dx, which in this case is e to the integral of 1 over x plus 1 dx. That integration is simple. What is the integral of 1 over x plus 1 dx? Is simply the natural logarithm of the absolute value of x plus 1. So we know that e to the natural logarithm of u is simply u. So here we simply get x plus 1 it could be plus or minus, requiring that this be a positive number. I'm being relaxed here regarding sign. I'm treating this symbolically. Okay, so now I'm multiplying both sides of my equation by mu. So we get x plus 1, x plus 1 y prime, plus, when I multiply x plus 1 times 1 over x plus 1, they cancel out. So you end up with just y equals to x times x plus 1. Okay, recall that this is now just the derivative of a product. Which product? Mu, which is x plus 1 times y. So you have that equals x plus 1. Now, what we want to do is to solve. This is a differential equation. This is a derivative with respect of x, but it is separable, so we separate the variable. Let me write it more suitably. The independent variable here is the x. So let me write this left-hand side more suitable using differential notation. So you get the derivative of x plus 1, y with respect of x equals to x plus 1. Now we separate the variable. This is mu y. You can view this as a single variable. So this is you view this as d of x plus 1y as a single variable equals to x that's x squared plus x dx. Now, as a separable equation, we can solve it by integrating each side. The integral of the differential of this variable is simply this variable, x plus 1y. And then the integral of x squared plus x is going to be x cubed over 3 plus x squared over 2 plus some constant of integration. If you want y by itself, all you have to do is divide through by x plus 1. If you want to have a single fraction, then you should write the right-hand side with the common denominator of 6. So you get x cubed times 2 plus x squared times 3 plus some constant of integration. This formula will be 6c. So if you permit me to write c1 here, then I can say this is c, where it's just 6 times c1. It's just a constant. So I'm calling it c. That's c1, this guy is c. And then since we are dividing both sides by x plus 1, we end up with this answer. Y equals to 2x cubed plus 3x squared plus c all over 6 times x plus 1. Okay, next example, y prime equals 1 minus 2y times x. The way it is written right now does not reveal whether it is a linear equation on y. But let's see if we can try to fit the frame. See if we can make it look like a generic linear equation in y. So what we would like to do is we would like to have our first derivative together with y. So distributing the x's in order. So you distribute the x, y prime equals to x minus 2yx. And I would like to put y prime and y together, so I'll bring the 2yx to the left side, so add 2yx on both sides. So what do you get? You get plus 2yx. I want to put the x in front of the y equals x. Oh, forgot the y prime. So y prime plus 2yx equals x. So it is linear on y. Okay, so now we know what to do. We need to find mu. Incidentally, mu is called an integrating factor of this differential equation. So let's find the integrating factor. Recall is e to the integral of px dx. In this case, p of x is 2x. So this is e to the x squared. When you integrate 2x, you get x squared. So multiply both sides by e to the x squared. So you get e to the x squared y prime plus 2x e to the x squared y equals x e to the x squared. Of course, we know what this is. This is the derivative with respect of x of the product mu y. Mu in this case, so is the derivative of mu y. But mu, we know, is e to the x squared. So put, that's my mu, that's my y. This is the function x e to the x squared. Okay, now we want to separate the variables. So we obtain d of e x squared y equals to x e x squared dx. time to, so we separated the variable, so now it's time to integrate both sides. When we integrate the left-hand side, we simply get e to the x squared y. So e to the x squared y. The right side, it might seem a difficult integral, but if you make a substitution, if you let u equal ex squared, so let u equal to ex squared, the derivative with respect of x is going to be e to the x squared times the derivative of x squared, which is 2x. As you can see, we don't have 2x, but we can make it. We can put a 2 there and a 1/2 there. So we end up with e to the x squared times y equals to 1/2. So this is my u. 2x. If I solve for the u here, you get 2x e to the x squared dx. This is my d of u. This is my d of u, this whole thing. I was a little bit confused there, right? So du equals 2x e to the x squared dx. So that's just du. We know how to integrate du. It's simply u. There is some constant of integration. I'm going to call it C1 for now, just in case I need to dress it up. I'm going to back substitute now. It's e to the x squared. So e to the x squared y equals to 1/2 e to the x squared plus C1, which I'm going to call C/2. And the reason I'm doing that is because I would like this to be a single fraction. So I get y equals to, if I divide both sides by e to the x squared, I end up with y equals 1/2 plus C/2 ex squared. Let me put this in the numerator. So I end up with y equals 1/2 plus C/2 e to the negative x squared, which you can simply write as a single fraction. 1 plus c e to the negative x squared over 2. Okay, so a bit long. All right, let's do one more example and look at number 3. So could this be a linear equation on the variable y? Well, let's see. So here we have in number 3, y prime equals to 1 minus xy over x squared plus 1. I would like to bring this y together with the y prime to see if it fits the frame. So if you split this fraction up, you get 1 over x squared plus 1 minus xy over x squared plus 1. Bring it over, so you end up with y prime plus x over x squared plus 1. Y equals to 1 over x squared plus 1. So yes, linear on y. Integrating factor mu equals to e raised to the integral of p of x. That's your p of x right there. It is a, we can use substitution. Let u equals x squared plus 1. Then du is 2x dx. I basically have it here except for the 2. So let's just put it in there. So this is e 1/2 2x over x squared plus 1 dx. So if this is u, that's the u. So that's what you obtain from that is basically e to the 1/2 ln of x squared plus 1. And you can put that as an exponent, that half as an exponent. So you end up with e to the ln of x squared plus 1 to the 1/2. E of ln cancel out, so you end up with simply x squared plus 1 to the 1/2. Or if you wanted square root of x squared plus 1. Maybe we use this or maybe we use that. Okay, so let me write one more step in this presentation. We can leave the rest of the details for the audience. So now we have, remember our differential equation is that right there. We're multiplying it by, we're multiplying both sides by mu, and the mu turned out to be this expression right here. So I end up with x squared plus 1 to the 1/2 y prime plus x squared plus 1 to the 1/2 over x squared plus 1 y equals, I figured that there is going to be some cancellation somewhere. So here we have x squared plus 1 to the 1/2, and there you have x squared plus 1. So there is some cancellation here. This is the power 1, this is the power 1/2. So I can just write 1 over x squared plus 1 to the 1/2. Similar situation here, although I wouldn't worry too much about the left hand side because we know what it is. That's just the derivative with respect of x of mu, which is square root of x squared plus 1 times y, which is what you obtain there. On the right side, we will get the 1 over square root of x squared plus 1. When you separate the variables, you end up with d of square root of x squared plus 1y equals to dx 1 over x squared plus 1. Now it is a separable equation. Now we have to play the game of, do we know how to integrate? Well, that one's simple. So it's just square root of x squared plus 1y. This one, it's not immediately, it's not simple, it's not readily available unless you know several formulas for integration. But when you look at the form, you see that you can perform a trig substitution. So I'll pretend that I know how to do this. It might take a little bit of effort to obtain, but you will get this by using some method of integration. I'm thinking of trigonometric substitution. Once you get that integral plus your constant of integration, to obtain y is just a matter of dividing both sides by the square root of x squared plus 1. I'm going to stop this video at this point. I believe that we have a good introduction to solving linear differential equations, first order linear differential equations. Something interesting just occurred to me. Out of the 3 examples we worked on, I didn't see one that was not. So this question may be redundant unless these pending questions will be illustrative of that. Maybe number 5. I see number 5 is not going to be linear because of the y squared. Okay, that's all for now.